Okay, so let's include this last piece just as an example of where we are in terms of actual simulations. There is also lots of literature on MJO predictions and predictability, which I'm not going to go into in this series. But let's first add a little bit about the different convective schemes and how they do the northward propagating MISOs. So we will look at some MISO model renditions and then MJOs. So to start with, just to orient ourselves, this is a model study that took one model, I think it's CFS, and then took multiple cloud microphysics and convective schemes and looked at things like the active and break periods and the difference of active minus break. So this is the observations as seen in GPCP, Global Precipitation Climatology Project, and these are the different parameterizations that were tried. NSAS with no ice, NSAS with ice, SAS no ice, SAS ice, and then recommendations are made in how to improve the microphysics to improve the rendition of the active break periods and the MISOs. Looking at the results of MISOs, here are the lag longitude section of regressed 10 to 20 day filtered daily anomalies averaged over 10 to 20 north. So looking at the observations again, you see the lead lag relation. Obviously 0 is where the convection or precipitation is maximum on the core monsoon zone, and you look at the different parameterizations and they are quite different than the observations. So the idea is that you compare the microphysics and then try to see how the microphysics can be improved, and the same thing we looked at for different convective parameterizations from a regional Earth system model and showed that improved resolution improved the northward propagation a little bit. So that kind of remains the story with CMIP5 and CMIP6 as well, as we will see in a minute. And going back to the laser pointer, lag latitude section of regressed 30 to 60 day filtered daily anomalies. So now you see averaged over 70 to 90 east. So this is the Indian longitudes, and you can clearly see the northward propagation here. This actually goes onto the Bay of Bengal, and you compare it to different microphysics, and again significant differences in terms of where the maximum happens. So here this is showing in tropical maximum amplified on the Bay of Bengal for both the break period and the active period, whereas here you can see that the break period and active period are not having this kind of continuous link to the tropical region as we see in the observations. Of course, one can do this with just land precipitation, because often there is argument that the precipitation data over the ocean is not as reliable, but nonetheless when you do this you try to understand what is missing in terms of processes over in the tropics and in the into the edge of the tropics over the Bay of Bengal. Okay. This is now looking at a paper that's looking at CMIP6 models for intraseasonal rainfall variability over the monsoon region. So this is from the IMD data for June, July, August, and September. So you have the onset, and the June contributes about 20% to the seasonal total. July and August are the peak seasons, and September is where the withdrawal happens. And without even saying which model is which, you can see that each model is different, but also not very good in terms of correspondence with the IMD data, even though IMD data is only on land, so it misses the coastal ocean maxima that's seen in observations, which you would see in satellite data or GPCP and so on. So that kind of screws up this figure a little bit, but you can nonetheless see that the distribution of rainfall over the Western Ghats versus peninsular India and core monsoon zone is different in each model for June, for example, and the same thing for July and August and September. So the withdrawal and onset are also not as well done in models. So the point is not to say models are no good, but the point is to say look at the models and kind of try to look at the dynamic consistency between the models in terms of how the onset in the model corresponds to its withdrawal, length of the rainy season, rainfall distribution in terms of number of rainy days, frequency, intensity, and so on and so forth. And one can also look at the temporal evolution of the different models. So again, for June, July, August, September, B, C, D, E. And in each one the IMD data is shown in this blue color, and you can see that models do not agree with each other and they don't agree so well with the IMD data. For example, here this green model, which is BCC SMI, is better compares to IMD, but this model BCC CSM2 is down here, so very, very different rainfall amounts. So again, northward propagation speeds and the amount of rainfall they bring and the distribution of low pressure systems, active break periods, everything is kind of imperfect in the models. Doesn't mean they are wrong. They do capture a lot of the features, and the question that's being always asked of newer versions of CMIP models is whether CMIP6 got better than CMIP5. CMIP5 models were compared with CMIP3 before, when the last AR5 came out in 2014, and so on. This paper looks at MJOs, just to move from MISOs to MJOs. So looking at, so this paper focuses particularly on how the maritime continent crossing by the MJOs is done in CMIP6 models and whether they have improved over the CMIP5 models in terms of transitioning across the maritime continent into the West Pacific. So here is what TRIM shows in terms of lags again. So you can see that's where the maritime continent is, and CMIP5 models were doing it this way with the weakening of the MJOs over the maritime continents, whereas CMIP6 mean seems to have improved, and individual models have different level of variations of variance and variability over the maritime continents, but this is kind of the mean. So people often look at multi-model ensembles which tend to be better than individual models, and there is physical reasons why multi-model ensembles give better skill, not only in simulations and projections, but also in terms of forecasts, which we will not get into here. This paper looks specifically at what happened at the processes. So it looks at the 850 to 700 hectopascal integrated specific humidity in ERA5, which is a reanalysis product, and at CMIP5 models and CMIP6 models, and looking at the mean state difference and the zonal and meridional gradients. Because there is work before by Dae-Hyun Kim, who is a co-author on this paper, arguing that the meridional and zonal gradients of the humidity is critical for detouring the MJOs. Many of the MJOs get stalled here. Some of them cross but weaken. Some of them cross and are reborn here, and some of them get detoured. And we have mentioned before that the barrier to the propagation includes the mountains here, the land-ocean contrast with some 22,000 islands, the heat capacity of land versus ocean, the diurnal cycle which takes away energy from the MJOs, and so on and so forth. And the idea is that the CMIP6 models are doing the meridional and zonal gradients of humidity better, and that is how they are improving the MJO simulation across the maritime continents. Okay. Another paper looked at the variability of MJOs in the models and compared them against data, and here are the multimodal ensemble mean for different regions. So this is for Amazonia, and you can see models are weaker. Over Southwest Africa, this is the observations, this is the multimodal ensemble, almost non-existent compared to observations. And comparing again over the maritime continent region, here are the observations and here are the multimodal multimodal ensemble mean. And again, even though here it's argued that CMIP6 models have gotten better in transitioning across the maritime continent, they do it with a reduced variance compared to observations. Okay, so they're getting better, but still have some ways to go. So this is how models are doing, and the reason for improved simulations come from various things like improved resolutions, improved parameterizations of maybe convective momentum transport, dilute plume approximation, and other details which we didn't get into. But also many of these models are the so-called Earth system models, which have all kinds of feedbacks, vegetation and carbon feedbacks, and it's not always clear whether those kind of Earth system feedbacks also can help improve the interseasonal oscillations. That's a separate topic, and it has been looked at in terms of the ability of the vegetation over India, for example, to take up moisture during the active period and give it back during the break period, which improves the simulation of precipitation during the break period over certain parts of India. So that's a very clear kind of feedback that's not always evaluated, even though it's included. So in the case of cyclones, for example, the model